we're going to take a look at the idea of the distance formula and the midpoint formula with respect to Cartesian plane and what this really means to us. Before we can do that, one of the algebraic techniques that we have to be cognizant of is how to simplify square root expressions where we have a number underneath the radical. And it's not too difficult to do that if you're pretty good with your multiplication facts. Basically, what we're going to do is we are going to factor a number into a number that is not a perfect square and the one that is a perfect square. And then we're just going to take the root of the number that is a perfect square, and we're going to leave the term that's not a perfect square under the radical. For instance, a really easy example of this is the square root of 24. So we know that 24 can be factored into, obviously, 1 times 24, 2 times 12, 3 times 8, and 4 times 6. And of all of those sets, the only one that's a perfect square is 4. And remember, a perfect square is a number that when we square it, when we square some number, we end up getting that value, which we think is a perfect square. So what we're going to do is we're going to pick those two numbers, 4 and 6, and we're going to factor 24. So we're going to turn this into 4 times 6. There's a rule of algebra that says we can split this up into the square root of 6 times the square root of 4. And we know that the square root of 4 is 2. So we can write this as 2 roots of 6. So that's how we can go ahead and simplify a radical expression. We're going to factor it. We're going to just split it apart using this rule of radicals. And then we're just going to take the square root of something that we can take the square root of. Right? A second example is going to be the square root of 150, a little bit bigger number. And it might be good for you to go ahead and go down the list of numbers that might be perfect squares and start thinking of it that way. So we certainly know that 1 is a perfect square, but 1's never going to help us, right? Because that's going to give us 1 times 150, and we're in the same boat we started with. All right, so I wouldn't even worry about using 1. Another perfect square is 4, all right? But I don't believe that 4 evenly divides 150. 9 is another perfect square, but it doesn't evenly divide. 16 is another perfect square, but it doesn't evenly divide 150. And if you're not sure, what you could just do is bring up your calculator, and you could do 150 divided by 4, all right? And that gives you a decimal number. So if you get a decimal number, it's not evenly divisible. If you tried 150 divided by 9, again, not divisible cleanly. 150 divided by 16, not divisible cleanly. 150 divided by 25, though, is. All right, so 150 divided by 25 is 6. So that means 6 times 25 is 150. And so those are our magic numbers that we're going to use, is 25 times 6. And so we can rewrite 150 as 25 times 6, or root 25 times root 6. We know the square root of 25 is 5, and we don't know what the square root of 6 is. All right. Now, there are some numbers that are sneaky, like 72. All right. And let me explain why 72 is sneaky. All right. So we're going to go back to our calculator. And we know that if we took 72 and we divided it by 4, that would give us 18. So one might think, okay, well, 72 is 4 times 18. Those are magic numbers. And so I'm going to put that under the square root. And so the simplified version of that would be 2 roots of 18. But unfortunately, that's not completely simplified. All right. And the reason is because isn't it true that if I was to go into my calculator and take 72 divided by 36, that's also a perfect square, 36, which evenly divides 72 into 2. All right. The reason that this isn't simplified is because 18 contains another factor within it. So this isn't completely done. So we could rewrite 2 times 18, and 18 is equal to 9 times 2. This would be 2 root 9 times root 2, 2 times 3 times root 2, or 6 roots of 2. However, if we would have just picked at the beginning 36 times 2, we could split that up into 36 times 2, or root 36 times root 2, and that also gives us 6 root 2. All right, so One of the concerns is that when you're trying to work with these radicals is to always try to pick the highest perfect square, all right, to be able to factor into. And like I said, 72 is a sneaky number because we know that 72 is both 4 times 18, but it's also 36 times 2. So you always want to pick the highest perfect square if given the opportunity to simplify. So the whole reason that we need to be cognizant of simplifying these sorts of radical expressions is because sometimes when we use the distance formula, we have to simplify at the end. And so what we're going to do is we're going to take a look at what the distance formula is and how we can compute the distance between 2 points. So let's say we have a line segment, and let me just draw this out. We have a line segment, and let's say this is the initial point. Let's call it x1, y1, and this is the terminal point. Let's call it x2, y2. If I wanted to find the distance of this line segment, then what I'm going to do is I'm going to use this formula. So I'm going to take the difference of x2 minus x1. I'm going to square it, and then I'm going to take the difference of y2 minus y1. I'm going to square it, and then I'm going to take it underneath the radical. And that's where we might need to do the simplification. Sometimes it's going to work out perfectly, sometimes it's not. Okay, so we'll get there when we cross that bridge. So let's do a few example problems in which all we're going to do is just go through and use the distance formula. And then if we're going to simplify it to get an exact answer, but we're also going to get an approximate answer, accurate to 2 decimal places if that's necessary, right? So we have the points 1, 3, and 13, 8. One of the things we can do is we can just start by labeling x1, y1 as 1, 3, and x2, y2 as 13, 8, and we can throw it right into the distance formula. So x2 is 13, so we're just using our formula. So we have 13 minus x1, which is 1. We're going to square that. And then we have y2, which is 8, minus y1, which is 3. We're going to square that. We're going to compute what's in the parentheses. So we just use our order of operations. So this is going to be 12 square plus 5 square. We're going to use our exponents. So that's going to be 144 plus 25. We know that 144 plus 25 is the square root of 169. And what we should do is let's just use a calculator to see whether or not that's a perfect square. Some of us might or might not know it is. So we're going to take 169 in our calculator. We're just going to find the square root of that. This is a button right here, second root, and it's 13. So it's a precise integer value. Okay, so we don't need to simplify that one. All right, that's nice that we didn't have to do some of the stuff that we just looked at up here. Sometimes they don't work out precisely. So let's take a look at a secondary example. So we have their distance. And again, we can label as x1, y1 for the first coordinate and x2, y2 for the second coordinate. And so I'm going to have -4 minus that -8. And I'm going to square it. Right? So that's x2 minus x1 square. And then we have 3 minus a -3. And we're going to square that. All right. Now we just have to be careful with our signs. All right. Now notice this just becomes a positive and this becomes a positive. So we have -4 plus 8, which is going to be 4 squared. And then we have 3 plus 3, which is going to be 9 squared. That's going to turn into 16 plus 81. Oh, I'm sorry. That's going to be 6 squared. Excuse me. All right. So that's going to be 6 square, and then that's going to be 36. So we end up with 52 under the root. All right, now 52 is not a perfect square. All right, and how do we know that? Because we go into our calculator and we just type in 52. We take the square root and we get 7.21, which is one of the things that we have to do. Remember, the question asked us to approximate to 2 decimal places if necessary. So we can say immediately that that's going to be 7.21. And that's part of the answer that we're looking for. But then we have to go ahead and factor this. All right, so let's go into our calculator, and we're going to have 52 divided by our first perfect square, which is 4, and that's 13. All right. Now we could go ahead and we could try a few of the other perfect squares, like 52 divided by 9. It doesn't give us a nice integer answer. 52 divided by 16. That's not going to give us a perfect integer answer. 52 divided by 25. All right. And we could try 52 divided by 36. And clearly now we're getting to the point where if you're getting down to 1, you're not going to get anything like perfectly divisible. Like 52 divided by 49 would be the last one. When this number gets really close to 1, that just means that you're approaching the number you're trying to divide into, and it's not going to make much sense. So the best pair we can get out of this is that 52 is equal to 4 times 13. 4 is a perfect square. So we're going to take the square root of 4 times 13, which is square root of 4 times square root of 13, or 2 roots of 13. All right, so now we have the approximate and we have the exact value for this. Right. When you get the decimal numbers, you can just go ahead and compute it really quickly without even having to worry about simplifying. The only time we're going to simplify is if we have integer values or whole number values underneath the radical. Sometimes it is possible, but we're not going to worry about those to be able to simplify the decimal sorts of values under the radicals. So we're going to label this x1, y1, x2, y2, and we're just going to substitute it into the distance formula again. So we're going to get 2.1 minus 0.5 squared plus 3.2 minus a negative 0.7 squared. And we're going to compute. All right, now this is just going to turn into minus a minus is a positive right here for this third 3.2 minus 0.7. So we're going to end up with the square root of 1.6 squared plus 3.9 squared. Now in our calculator, let's just compute those. Okay, so we have 1.6, now we're going to square it. That's 2.56. And we have 3.9 squared. And that's going to be 15.21. Right, we're going to add those together. Right, and if we add those together, we can do that really quickly. That's going to give us 1777. And at that point, we're just going to go ahead and find the square root of 17.77. And that's going to give us, well, if we take the square root of that, that's going to give us 4.22, approximate to 2 decimal places. All right, so that's how we can go through and find the distance. And remember, this just represents the distance between these 2 points and the distance between these 2 points. So here's an approximation. Here's the exact value. The midpoint formula is even easier. The midpoint formula is basically the average distance. Okay, so we're going to add x1, we're going to add x2, and we're going to divide by 2, and y1 plus y2 divided by 2, and that's basically going to figure out the midpoint of a line segment. All right, so geometrically, right here, approximately is going to be the midpoint of this. If this is going to be x1, y1, and it's going to be x2, y2. All right, so let's go ahead and just evaluate a couple examples where we find the midpoint of a line segment. We can again label as x1, y1, x2, y2. And for us, the midpoint for this is going to be -5 plus -9 divided by 2, and then -6 plus -8 divided by 2. All right, and then we can just crunch this out. That's going to be -14 over 2. And then we're going to have comma, another -14 over 2. And that just winds up to be the point -7, -7. Right? We don't always get the same coordinates for x and y as the midpoint. It just happened to be that way for this one. Even if we have some fractions going on, we could still find the midpoint of these sorts of fractional coordinates. So again, x1, y1, x2, y2. And so we plug it into our formula. And we're going to have x2 plus x1. So that's -1/2 plus -3/2 divided by 2. And then y1 plus y2. All right. And by the way, since addition is commutative, it doesn't matter which order we do these in. All right. So I think I flipped the order x2 plus x1. It's perfectly fine. All right, so this is going to wind up being 3 halves and negative 13 halves, and we're just going to add those numbers together. So we have 3 over 2 plus a negative 13 over 2 divided by 2. We're going to compute. So we have negative 1 half plus negative 3 halves, which is negative 4 halves over 2. And then 3 minus 13 halves is going to be a negative 10 over 2 divided by 2. Right? If we simplify just a little bit more, we know that negative 4 over 2 is negative 2. And we know that negative 10 over 2 is negative 5 over 2. And then the last thing we could do is just simplify this negative 2 over 2. So the midpoint is going to be negative 1, negative 5 halves. Right. So hopefully that gives you a good overview as to the distance formula and the midpoint formula, and also simplifying radicals. In our next video, what we're going to do is we're going to start taking a look at equations of circles, which is another sort of application we can look at in the Cartesian plane.